Here we're going to talk about another operational amplifier called a summing amplifier, or also known as summing inverter or even voltage adder. Before we get into the tricks of simplifying this circuit, we're just going to solve for V out using my favorite nodal analysis. While you can use any method to solve this, I think nodal analysis is the easiest, at least for me. So solving for V out, you're going to have Vn minus V1 over Rn plus Vn minus V2 over Rn plus Vn minus V3 over Rn plus Vn minus V out over Rf, all equal to 0 using nodal analysis. Because we know that Vn is equal to Vp, and we know that Vp is just grounded, so it's going to be equal to 0. Therefore, all the Vn's can be substituted with 0. Moreover, because all the resistors on V1, V2, and V3 are the same, you can do some substitution, and you're going to end up with V out is equal to negative Rf over Rn times V1 plus V2 plus V3. Inserting the values for V1, V2, V3, and the resistor values, you get negative 18 volts. If you try both equations, you'll find that they're equal. Moreover, the gain of this circuit is equal to V out over V in, which is equal to negative Rf over Rn. Using the resistors, this is equal to 2K, negative 2K over 1K, which is negative 2, and then V out over Vn is negative 18, with Vn being the sum of all the resistors, which is V1 plus V2 plus V3, 4 plus 3 plus 2, which is equal to 9, which is also equal to negative 2. V out can also be written as the gain times the sum of the voltages in this configuration when all three resistors are the same value. Let's look at another configuration called a scaling summing amplifier, which the input resistors are not equal. So in this case, when we solve for V out, we're going to have negative Rf over R1 times V1 plus negative Rf over R2 times V2. This can also be written as the first gain times V1 plus the second gain times V2. Substituting these values, we get 10K over 1K times V1, which is 2 volts, plus negative 10K over 2K for R2 times V2, which is 3 volts, which is equal to negative 35 volts. Next, we have a non-inverting summing configuration where the summing is occurring in the positive terminal. Alright, so solving this circuit, we can start with the same thing as before, where we're going to have Vp minus V1 over R1 plus VP minus V2 over R2 is going to equal 0. And this is equal to 0 because the current with resistor 1 plus the current resistor 2 is going to be equal to 0 because of KCL. Solving for this, we're going to have VP minus V1, which is 2 volts, over R1, which is 1K, plus VP minus V2, which is 3 volts, over R2, which is 2K, is equal to 0. Solving for this, we're going to get VP is going to equal 7 over 3, or 2.33 volts. So we know that VP is equal to VN. So now our VN we're going to solve for to get V out. So we have V out, which is the voltage drop across this area, right? It's the voltage drop across the two resistors, R3 and R4. And then our VN, right? This point, we're just going to have the voltage with R3. So this equation, you're going to have, so Vn is equal to Vp. So then you'll have V out is going to equal to Vp times the voltage drop, which will be R3 plus R4 divided by R3. So V out finally will equal 7 over 3 times R3 plus R4, which is 7K, divided by R3, which is 4K, which equals 7 over 3 times 7 over 4, which is equal to 49 over 12, or 4.083 volts. Another way of looking at this is that we know from a non-inverting amplifier that the formula is V out equals 1 plus RF over Rn times Vin. In this case, RF is R4 and Rn is R3. Therefore, we have V out is equal to 1 plus R4 over R3 times Vn. And in this case, our Vn is Vp. We found our Vp to be 7 over 3, so we have V out is equal to 1 plus R4 over R3, which is 3 over 4, times Vp, which is 7 over 3, which equals 4.083 volts, our same answer. One case is if R1 is equal to R2. In this configuration, you know Vp is going to equal Vp minus 2 over 1K plus Vp minus 3 over 1K, which is equal to 0, like we did before. Solving this out, you're going to get Vp is equal to 5 over 2. If you rearrange this a bit, you actually just get Vp is equal to V1 plus V2 divided by 2 using the voltage divider. Then using our previous formula, we'll have V out is equal to 1 plus R4 over R3 times VP, which is V1 plus V2 over 2, which is equal to 1 plus R4, which is going to be equal to 3K, divided by R3, which is 4K, times V1 plus V2 over 2, which we said was 5 over 2. And your final answer is going to be 35 over 8, which is equal to 4.375 volts. And then our final configuration here that you should recognize is when R1 is equal to R2, which is equal to R3, equal to R4, and they're all 1K. Using our formula from before, we would have V out is equal to 1 plus R4 over R3 times V1 plus V2 over 2. Substituting the resistor values, you're just going to have 1K over 1K, so you'll just have 1 plus 1 times V1 plus V2, which is going to be 5 over 2. This simplifies to 2 times 5 over 2. The 2's cancel, and you're left with 5, which is just equal to V1 plus V2. So when you have a summing amplifier with all the resistors, and this 4-resistor setup, being the same, you can simply recognize that the output voltage is going to be V1 plus V2. This concludes our video on summing operational amplifiers. Be sure to like and subscribe, and check out our channel for more videos on op amps.